We're asked to determine the interval where f is increasing or decreasing. So you could graph it, you could determine it that way, or you could do it algebraically by finding the first derivative. So the power rule happens. And increasing means you have positive slopes. Decreasing means you have negative slopes. So I'd want to find out every place where I switch from having negative to positive or vice versa. I want to find all the values that are positive for the first derivative. So set it equal to 0. This is quadratic. Can we factor it? 3, 2. I think we can factor this because this is factoring when the leading coefficient is not 1. So you got to multiply. Here, this might ring a bell. If we rearrange it in order of descending powers. To factor this, we multiply the leading coefficient and the last number that doesn't have an x. And your goal is to find two numbers that multiply to be -3 but add up to be 2. So how about 3 and -1? Because then we can replace the middle term with that pair and then factor by grouping. You can pull out a 3x from the top, so that's -x plus 1. And over here, when we put a group around these two, that's already -x plus 1. It's the same thing. So final step for factoring by grouping is that you can put a 1 out front of there as a coefficient. You can factor out the -x plus 1 from everything. So you've got 3x plus 1 and -x plus 1. So if you had trouble with that, that's factoring quadratics when the leading coefficient is not 1. That's what you'd want to Google. Or you could use the quadratic formula. Okay, you're going to get the same thing if you use the quadratic formula. Because the last step to solving is to set each factored piece equal to 0. And when you do that, you get x is -1/3 and x is 1. So those are the two places where we could switch from being positive or negative or vice versa. So to check to see whether whether we're increasing or decreasing, you'd want to maybe make a number line. Here's one potential switching place. Here's another potential switching place because that's where it hits x equals 0. And you want to test numbers in between these, okay? So you want to test something in between these two, something to the left, and then something to the right. So if I plug in x equals 0, if I plug 0 into this function, into the derivative, I get out a positive 1. So it's positive in between -1/3 and 1. And if I plug in like -2, something to the left of this value, -2 squared is 4. 4 times 3 is 12. So -2 times 2 is -4. -4 minus 12. This is going further back in the negative, so it's negative over here. And if I test a value to the right of 1, let's just grab x equals 2. You can plug in x equals 10 or whatever you'd like. If you plug in x equals 2, 2 squared is 4. 4 times 3 is 12. So 2 times 2 is 4. 4 minus 12 is negative, and plus and 1 isn't going to matter. It's going to be negative over here. Okay, so we have all the intervals where it's increasing or decreasing. Remember, this is the first derivative. So the first derivative is negative over here, and it's negative over here. That means it's decreasing in those places. It's decreasing. I don't want to. This isn't for part B, right? Decreasing from -infinity to -1/3, and then also from 1 to infinity. It's increasing between -1/3 and 1. Okay, because we found the first derivative, we found all the positive slopes. Local minima and local maxima. Here, I'll put this graph back on because a local minimum happens when you switch from being negative to positive in your first derivatives. That's because negative on the first derivative means you're going down. And then if you switch to having positive values, then your original function starts going up. So if you go from negative slopes to positive slopes, you've hit a local minimum. And remember, that has to be read left to right. And vice versa is true. If you have positive slopes and then negative slopes, you've hit a local maximum. So I can type that up as a quick rule. Local max, you switch from negative to positive derivatives, first derivative. And then local min, that's a local min. From negative to positive, I got those reversed. That's a local minimum. And local max is just the opposite. Switch from pos to negative first. Okay, and remember that's read left to right. You're reading that left to right. You're reading this number line left to right. So local minimum, we switch from negative to positive at negative 1/3. So negative 1/3 is a local min. And we switch from positive to negative at x equals 1. So 1 is a local max. And those are the only two places where we switch. Okay, let's get rid of all this, because the next part asks us for where f is concave up or concave down. So concavity is talking about the second derivative. I deleted my first derivative, but I can get that back real quick. So here's my second derivative. That's 0. This is 2, and this is 6x. So I want to set the second derivative equal to 0, again, just like I did with the first derivative when I was trying to find local max and local mins, because that tells me the only places where I could switch from negative to positive or vice versa. Okay? So we got 2 minus 6x. We want to set that equal to 0 and solve. Subtract 2 from both sides. Divide both sides by negative 6. You're going to get x is 1/3. So that's the only potential switching point. We want to check on a number line what this function, what the second derivative is doing. Here's 1/3. Doesn't have to be perfect. So you want to test a value to the left, test a value to the right. I'm going to test x equals 0. If I plug 0 into my second derivative, I get out positive 2. So it's positive everywhere over here. And if I test out a value to the right, let's try x equals 1. If I plug in x equals 1 in here, that's 2 minus 6 makes a negative value. It's negative everywhere to the right of 1/3. And again, this is the second derivative. So what that means is that it's concave up between negative infinity to 1/3. And it's concave down from 1/3 to infinity, because the slopes, the slopes of the slopes. And the second derivative is negative to the right of x equals 1/3. That's why it's concave down. It's concave up between negative infinity all the way to the left up until you hit 1/3, because we're getting positive slopes. And x equals 1/3 is the only place where we could switch from being positive to negative. Inflection points are where we switch from a positive to negative on the second derivative. So that's 1/3 for this one. And from positive to negative, or vice versa. An inflection point also happens if you switch from negative to positive on the second derivative. Inflection points are about the second derivative. They're about concavity.